Hello everyone, and welcome to this video titled Related Rates. So in this video, I'm going to be taking you through a preview version of a Knewton Alta homework assignment, also titled Related Rates. So please understand that this is a preview version of the assignment, and that the questions I work on in this video may not be exactly the same questions that you will see when you work on the assignment yourself. But all the objectives should be the same, and the methods used to solve certain problems should be very similar to the ones you're going to be using. And hopefully it helps you get through the assignment. Okay, so here we are, Knewton Alta, in section 4.1, this related rates section in the particular course of calculus I am teaching. In the upper right-hand corner, you should see a mastery bar that tells you how far along you've gotten in the assignment. Next to that, you have an activity log, which, if you click on it, shows you all of the objectives in the particular assignment. So this one has 6 objectives broken up into 2 headings. So we'll be taking through these 4 objectives here. Pardon me. Taken through these 4 objectives here before being moved into these 2 on related rates and other applications. I do have it set up where you could switch to the other heading whenever you wished, but I will not be doing that in this video. Alright, so then on the main page you have your current objective, a question related to that current objective, and at the bottom of each question you should see a feedback button. If you notice any issues with the question itself or the answer explanations after the question is done, you can send feedback directly to Knewton support, and they should get back to you relatively quickly and hopefully help you fix whatever issue you have. I hope you understand that the instructor cheat button will not be there for you. It's for instructors only to fill in answers for demonstration purposes. I will not be using this in this video either. But you will have and you will see the More Instruction button. So if you're working on an objective that you are unfamiliar with, or you don't recall the reading too well, or you just forget what to do for a particular kind of question, click here on More Instruction and go to Further Instruction, and they'll give you some reading to do or videos to watch, or both, related to that particular objective, and hopefully that'll help you get through the assignment. All right. So this first objective is express changing quantities in terms of derivatives. So the title of the assignment, the section, is Related Rates. All of these related rate problems, you will have quantities like area, length, width, whatever, volume, temperature. You'll have these quantities that are changing. They might be changing as time goes by or changing in relation to some other variable. But you'll have a relationship between quantities that are changing in relation to each other. Thus the name related rates. Their rates of change will be related in some way. So let's go through the question. So this first question says, suppose that the length L, width W, and area A, which is equivalent to length times width, suppose all these things of a rectangle are differentiable functions of t. So that means L, W, and A are all functions of this, time variable. Usually when t is there, I'll just think of it as a time. So area, length, and width of this rectangle are, changing as time goes by, right, as the value of t changes. Okay, so we're asked to write an equation that relates their rates of change, right? The dA over dt, remember this is the instantaneous rate of change of the area with respect to t, to dl over dt, again this is the instantaneous rate of change or the derivative of the length function with respect to t, and dw dt, again the instantaneous rate of change or derivative of the width function with respect to t. So write an equation that relates these when the length is 19 and the width w of this rectangle is 14. Enter your answers using exact values. All right. So again, here's, you have the area A equal to, the length L multiplied by, the width W, where each of these, A, L, and W, are functions of t, they say. So this means that as t changes, A, L, and W, will also change. Now, you could go through and replace them all with, this kind of notation. A is, A of t, some function of t. L is L of t, again, some function of t. And W here is, W of t. And that's what I'm saying by this. All of them are functions of this t variable that we don't know. We don't know what these expressions are. And they tell us also that these are differentiable. So what we do then, okay, you have this relationship between these quantities that change, with respect to a particular variable, in this case, t. So I have this equation relating the area, the length, and width of a rectangle. Area equals length times width. And area, length, and width separately, all depend on this t. So what we're going to do is set up an equation that tells us how fast, at what rates are these quantities changing as t changes with respect to each other, relative to each other. So we're doing implicit differentiation here. So this was something discussed in a previous video and in a previous Knewton Alta homework section on implicit differentiation. So we're going to do implicit, because notice that, we have expressions that depend on this t variable on both sides. So nothing in particular is, solved for. I know A is solved for here, but L and W, are also their own expressions depending on t that we don't know. So I'm going to do implicit differentiation, but with differentiation, sorry, with respect to this variable that every quantity depends on. So that's the variable t. So watch, right? So on the left side, I differentiate this area function with respect to t. So that will give me dA over dt. Right, that instantaneous rate of, now you could call this A prime if you wanted to as well. A prime of t would be the derivative of A with respect to t. That's all I'm getting from the left side. Now on the right side, this is a product of two functions of t, right? We have L of t times W of t. And I'm differentiating with respect to t, and so we have to use the product rule, which you should have seen plenty of times by now. So just write out what it is. So I got these two factors, right? This L of t and this W of t. It's from the product rule. When I differentiate, leave the first factor alone, so I'll keep the L function the way it is, multiplied by the derivative of the other one. And again, with respect to this variable t that it all depends on. And so L times, and then you could say this is W prime if you want. Just remember that it depends on this t variable. But I'll write it the way they have in the problem, the rate of instantaneous rate of change dW over dt like this. That was the first term, using the product rule. Then plus, and then the other way around where I leave the second factor the way it is, W, multiplied by the derivative of the first factor, which is going to be represented by, you could write L prime of t or L prime, but I'm going to write it the way they have it with the dl over dt. Okay, so this thing here that I just wrote out, this is what they're going to refer to as a related rate equation. Because it's an equation that shows you how the rates of change of these quantities that depend on time, that depend on t, are related at any given moment, right? So this is at any moment, at any value of t, the speed at which, you can think of these rates of change almost like a speed, how fast something's changing, the area is changing over time is how I like to think about it. So this right here is saying that at any particular moment in this, for this particular rectangle they're talking about, the speed at which the area changes, how fast the area is changing at any given moment, is equivalent to the length of the rectangle at that moment multiplied by how fast the width is changing at that moment, plus the width of the rectangle at that moment multiplied by how fast the length is changing at that moment, right? The speed at which the length is changing. And they give us, some information. They're saying, back in the question, it says write an equation that relates these rates of change, these speeds, at the moment when the length is 19 and the width is 14. So when the length of this rectangle is, 19 units, and the width of this rectangle is 14 units, here's how these rates of change, these speeds, how fast the area, width, and lengths are changing are related to one another. We have, the rate of change of the area is equal to, again, the length they're given to us is 19. So 19 times the rate of change of the width plus, and then the width they gave us, a particular width here was 14 times the rate of change of the length. So this is my answer. This is again the equation telling us how these rates of change are related at a particular moment when the length of this rectangle is 19 and the width is 14. So I'm just filling in those blanks. Now careful though, look, they have dl dt here. And the coefficient of dl dt was the width. So I'm putting 14 in this blank. Plus, and then the coefficient of dw dt was the length. So I'm putting 19 in this blank. And that, remember that sum was equal to dA dt in my equation. All right, then after you submit an answer, you'll be told if you're correct or incorrect, given some encouraging words. Then beneath, you'll always be given this answer explanation. Please read through these, whether you get it right or wrong. If you get it correct, you might still want to glance through the answer explanations just to see if they do something in a way that you like better, that's more efficient, and you may want to try that for future questions that are similar. Now, if you get something wrong, definitely read through the answer explanations carefully, and hopefully you can figure out where you went wrong, why you were wrong, and you can learn from your mistakes for future questions that are similar. So again, use related rates given an abstract equation. Right, so these are equations that are, abstract, not really related to any physical quantity or physical object like a rectangle. Nothing we can really picture. So look here, right? If z squared equals x cubed plus y squared, and dx dt, right? X prime of t. So notice how the denominator, the independent variable, what you're taking the derivative with respect to is t here, like in the previous problem with the area, length, and width. So all this here, the dx over dt is 2, dy dt is 3. Find, dz dt at a particular point, at the point where x and y are, 0 and 4. But notice again, the denominators in the derivatives here have the variable t. You're taking the derivatives with respect to t. So that's implying, right? We're doing implicit differentiation that x and y and z all depend on this, t variable. And we're trying to figure how do the rates of change, how do these derivatives relate to one another at any particular moment, at any particular point. All right, so I'll write the equation out and point that out again, that, these variables, all these quantities in the problem depend on another variable, called t, which you might like to think of as time. So we're given this equation, z squared equals, x to the third power plus y squared, where x, y, and z are functions of, and I'm assuming they are, differentiable functions, meaning, the derivative exists at any particular point. So I'm not going to write out the word differentiable every time. We're just going to assume it here. So x, y, and z are functions of another variable called t. So we take our equation and we do implicit differentiation. We're going to differentiate, and I'll just write diff with respect to, right, WRT, this new variable t. Now, if you'd like to replace, z with z of t and x with x of t and y with y of t, go ahead. I just find that to be a little more writing than is necessary. But we're going to do implicit differentiation, with respect to this t variable. So remember, anything that doesn't have t, which none of these do, you have to imagine are functions of t, expressions with t in it. So z squared is something with t, squared. So I have to do the chain rule here, right? The derivative of something squared is 2 times, that expression to the first power, but then times the derivative of the expression inside, which is this z expression depending on t. So then chain rule, I'm multiplying by the derivative of z with respect to t, which again, you can write z prime if you wish. It's just I'll write it out this way because that's the way they have it. And just also this reminds you that z is a function of t. So that's what I'm getting on the left side, equals, and then I'm doing something similar for each of these terms here, right? This x cubed term. Once again, x is a function of t. So this is something with t to the third power. So I do, power rule here, be 3 times x squared, but then times the derivative of the expression inside that power, which is x with respect to t, right? So times dx dt after. So again, chain rule. Now, if you want to write x prime, just remember that it's a function of t. That's fine. And then you do the same thing for the y squared, and for the y squared, it'll be pretty much like for the z squared earlier. You have 2 times y to the first, but then times the derivative of y with respect to this t variable, so times dy over dt. So once again, here is our related rate equation. One more time. All right, you have all these derivatives related to each other in some way. They must satisfy this relationship. Right, so here are how the rates of change, the derivatives, are related. Now, at the moment we are given. So this is a general equation, right? This tells us, and we should start general with these problems. This is a general equation, right? This is telling us how x and y and z and x prime and y prime and z prime are all related to each other at any moment in general. And then we go to the moment specific to us, to the problem, to the question. So start general and then plug in the specifics afterwards. So you go back to the information we were given. We were told that dx dt x prime at this moment we're looking at has a value of 2. And at the moment they want, dy dt or y prime has a value of 3. Z should be positive. When we do find z should be some positive value. And then we're asked to find the value of z prime or dz dt at the point where x equals 0 and y equals 4. So again, we're told that dx dt has a value of 2, dy dt has a value of 3. Z must be some positive value, and we'll find this in a second. And we're at the point where x and y are 0 and 4. Okay, so at this point, look at our equation. We can use this information to find the value of z as well. And then we'll have x and y and z. We'll have x prime and y prime. We'll have all the missing pieces to then help us find, dz dt, right? Because that's what they asked us to find, right? They said find that z prime or dz dt at this moment. So again, we have x, we have y. There are 6 unknowns in this related rate equation: x, y, z, x prime, y prime, and z prime. And we'll have right now we have 4 of them. X prime is 2, y prime is 3, x is 0, y is 4. And again, we can use this 0, 4 to find z. So go back to the equation. That was the original equation. We're on this curve, or this surface in space here, a graph involving x, y, and z would be a 3D surface. Z squared would have to be, at this point, 0 cubed plus, y is 4 squared. So z squared must be, 0 plus 16 must be 16. So z can either be positive 4 or z could be negative 4 as well. But remember what they pointed out in the question. They said z must be positive. So I'm going to, ignore the one where the value of z is negative 4. So now I have 5 of the 6 missing pieces. X is 0, y is 4, z is 4, x prime is 2, y prime is 3. We should be able to now find z prime. Right, this dz dt they're asking for by plugging in now to our related rate equation. So 2 times, so on the left here, 2 times the z value, right? So 2 times 4 times, this z, again, if you want to write z prime, that's fine, or dz over dt here, must be equal to 3 times x squared, right? So 3 times, x was 0, squared times, and then dx dt was given as 2, and then plus, and 2 times y prime. So 2 times 4, right, y was 4, and y prime, dy dt, was given as 3. So after all this, left side we have 8 times z prime, right, dz dt, equals, 0 plus, and then, 24, 2 times 4 times 3. And then I divide both sides by 8, and we've got it, right? They asked for dz over dt, or z prime, at this particular moment. Well, here it is. This is the rate at which z would be changing as t changes, at the same moment that this all stuff is happening. Right? So here's what we're entering, right? The value of dz dt is 3. So I'm just putting 3 in the blank here. No units involved. Wonderful. All right, so another one very, very similar to the last one. Just some different powers here, right? So it's z cubed equals x cubed plus y squared, if that's how x, y, and z are related. And say x and y and z are all functions of this t variable. And x, so at the moment where x prime is 3 and y prime or dy over dt is 2, and make sure z is a positive value again. find the rate at which z is changing as t changes, dz over dt or z prime of t, at the point where x is 4 and y is 0. So again, very, very similar to our last question. So here's the equation we're initially starting with. So again, z to the third power must be x to the third plus y squared. Once again, x and y and z all depend on this other variable called t. And so we go from our, before, I said this in the last problem, right? Before you plug in any specifics, we first establish the related rate equation. Differentiate both sides with respect to this t variable, right? How does a change in t affect both of these expressions? So I'm going to differentiate both sides with respect to this, t variable. I'm using the chain rule, right? Very similar to the last problem. So z cubed, again, that's something with p in it, cubed. So I would do power rule first, right? 3 times z squared, and then chain rule, multiply by the derivative of z. So dz over dt like this, right? Equals, and then again, same thing for the x cubed, be 3 times x squared, but then times the derivative of x with respect to this t variable. And then finally plus, and then same thing for the y squared, 2 times y to the first, but then times, through the chain rule, the derivative of y with respect to this t variable. Okay, so here it is, how x and y and z and dx over dt, dy over dt, dz over dt, all the rates of change, all these things are related at any given point, at any given value of t. All right, so now we go to, so again, we start general, right? You start general, don't plug in any specifics, and then you go specific. All right, so this is where I'm going to use, the given information. We're asked to find, once again, dz over dt, the rate at which z is changing as t changes, when, we're going to be given, the other 5 unknowns here. Right, there are 6 unknown values in this equation. We'll be given enough information to fill in 5 of these and then find, the missing 6th piece that they want. So again, they told us in the question that dx dt is positive 3, dy dt, the rate at which y is changing as t changes, is positive 2. They would like us to have z be a positive value, right? So when I go find z later, it should be some positive value. And then the x and y are 4 and 0. All right, so I'm plugging all this stuff in. We need to use this information though to find z, right? Because I have 1, 2, 3, 4 values. I need the 5th one to find the 6th one. I need z to find dz dt. Well, if x is 4 and y is 0, and this up here is how x, y, and z are related, we can find z. Right? So z cubed should be, 4 cubed plus 0 squared. So z cubed should be 4 cubed plus 0, 64, meaning z should be positive 4. And that's the only possible value, and that is positive, so that's good. All right. So now I have the 5 missing. I have 5 values out of the 6. Let's go find the 6th one now. So I plug all these numbers, 3, 2, 4, 0, and 4. into my related rate equation, and we'll be able to find, this dz over dt, this z prime, rate of change of z as t changes. So on the left side here, we have 3 times, z squared. So again, z is 4 times this, dz over dt equals 3 times x squared. So again, x is 4 as well, times, and then dx dt is given as 3 positive 3. And then I'm not even going to write in this last term because it's plus 2 times y, but y is 0. So it doesn't matter that y prime is 2. It's 2 times 0 times 2. So, it's plus 0, which is really unnecessary to write. So over here, if I were to divide both sides by this 3 times 4 squared, we end up with dz dt equals 3. The 3 times 4 squared would divide away. And I'm left with the rate at which z is changing as t changes positive 3. Which means, remember derivatives, when they're positive, the quantity is increasing. When they're negative, the quantity is decreasing. So, didn't really mention this in the last problem, but this would tell me that at this particular instant, right, at this specific moment here with all the information they gave us, the value of z would be increasing as t increases. Right? It's a positive rate of change, positive derivative. All right, but still, we're finding the value of 3 again there. Please understand that they're not all going to be 3. Right? It just so happened for these couple problems here in a row, the value of dz over dt here was 3. It's not always going to be that way. All right, so now we're into use related rates to solve problems involving area. Right, kind of like the area of a rectangle problem from earlier. Right, but this is a little more involved because you got to remember things. Earlier we were given that the area of a rectangle is its length times its width. But in some of these, you'll be expected to remember or be able to find certain formulas, right? For here, it's going to be involving the area of a triangle. So you see the base of a triangle is shrinking, means decreasing. So be careful when they talk about some quantity decreasing or shrinking. That means the rate of change, its derivative, right? The rate of change of that quantity as time goes by will be negative, right? Negative. And if anything is increasing, like the height, so the base of the triangle is shrinking at a rate of 9 centimeters per second, and the height of the triangle is increasing at a rate of 7 centimeters per second. So if a rate of change, is positive, then you're increasing, right? Increasing means a positive rate of change, whereas shrinking or decreasing will mean a negative rate of change, and I'll keep that in mind as we write things out. So we're asked to find the rate at which the area of the triangle changes when the height is 13 centimeters and the base is 4 centimeters. All right, so first I'm going to point out, hey, there are these quantities that are changing with time. And once again, I'll use the letter T to represent time. So the quantity is changing with time. You have the base of this triangle, which I'll call, just lowercase b. They mentioned the height of the triangle, the base is shrinking over time. They mentioned the height of the triangle, which I'll call lowercase h. They said that that was increasing over time. And then you have the area. All right, so the area I'll call capital A. So again, all these things are functions of t. They change as t changes. They depend on t, however you want to say that. So first we're going to write an equation. Or equations, you might have to write more than one on occasion, but an equation, or equations that relate these quantities. I'm going to write something that ties all these together. So hopefully you recall for a triangle. This is for a triangle. The area of a triangle is 1/2 times the length of its base times its height. So there's a little formula for you. It's like half a rectangle a triangle is, or half a parallelogram. Half base height. So just like before, now I have my general equation relating a bunch of quantities that depend on, t here. And then we'll go through and differentiate both sides with respect to t. How would these sides' values be changing? At what rates would they change as I change t? So I'm doing implicit differentiation. We're gonna differentiate both sides with respect to t. Like on the left side here, you got dt. Simple as that. Then over here on the right side, kind of like my rectangle problem earlier, this is a product of functions of t, right? The base is changing with time, the height is changing with time, so I have a product of expressions that are changing with time. So I'm going to go through the product rule. Now you could keep the half out if you want, which I might just do that. Keep the half outside, coefficients stick around, and then just do the derivative of this b times h and apply the product rule there. So remember the product rule, I'll leave the b factor alone, times, and then the derivative of h with respect to t, which again, dh over dt, or h prime of t. Then plus, and then the other way around, where I leave the h factor alone, multiply that by the derivative of the base with respect to time, so db over dt. So all this should be in parentheses though, because it's got to be multiplied by this half. Now if you want to distribute the half, you can, but I will leave it this way. So again, this is referred to once more because it's got these rates of changes, these derivatives, right? This is our related rate equation. Right? So the area of the triangle will change at a speed that is half of the quantity, the base of the triangle at that time, multiplied by how fast the height is changing at the time, plus the height of the triangle at that time, times, and then how fast the base is changing. Now we go to our specific moment. Now we were given the following information that I'm going to plug in here. There's a prime, b, h prime, h, b prime. There are 5 unknown quantities in this equation, this related rate equation. And I've been given enough information for 4 of them. And then we find the dt. And so back here we're told, remember we were told that the base shrinks, that's the key word, at a rate of 9 centimeters per second. So again, when you talk about shrinking, that's decreasing. That means dB, dt. Right, this is the rate at which the base is changing over time. That means the rate should be negative 9, centimeters per second. But I'm just going to plug in negative 9 for dB dt. And when quantities shrink, when quantities decrease, you got a negative rate of change. But the height, they said the height increased, was increasing at a rate of 7 centimeters per second. So again, increase means positive rate of change, right? So dH dt, and this is dH over dt here. Every time I go up on the h, it comes down, right? dH over dt. This is the rate at which the height is changing. And if it's increasing, if height is growing, then that means you have a positive rate of change. So positive 7 centimeters per second. But I'll just be plugging in 7 for dHdt. And we're asked to find the final part of the question, the rate at which the area is changing, right? So d capital A, dA over dt. At the moment, when the height is 13 centimeters and the base is 4 centimeters. Right? So they gave us all this information. So I'm just plugging that stuff in to my equation here. So at this moment, dA dt is half of b times h prime. So the base 4, h prime was 7, right? So 4 times 7, and then plus, and then the height times b prime. The height at this time was given as 13. And then again, b prime is negative because the base is shrinking. So times negative 9. All right, we simplify this. 4 times 7 is, 28. And this will be a negative, right? 9 times 13, that's 90 and 27. So that's 117. And 28, minus 117 be 89. But negative, right? So this is negative 89 halves. So there's A prime. Now the units on this, now they already have the units written in the answer part, but I'll explain. This should be a change in area over change in time. So change in area units in the numerator. So things were, length units were given in centimeters, so my area units will be in, centimeters squared, right? Square centimeters over, and then dt down here, time units, and all the time units given earlier were in seconds. So at the particular moment in question, the area is changing at a rate of negative, 89 halves, or that would be 44 and a half, negative 44 and a half square meters per second. And being negative means that the area would be shrinking at that moment. So you see, maybe it makes sense too that the area would be shrinking. is notice how, the base is shrinking at a faster rate than the height is increasing. Right, -9 centimeters per second versus +7. It's got a bigger magnitude, but in the negative direction. So maybe that makes sense if you think about a triangle where, think of a triangle where the base is getting smaller and smaller, right? This is going in, whereas the height's getting taller, but the base is getting smaller faster than the height is getting taller. So at this particular moment, hopefully it makes sense why the area would have to be shrinking. Anyway, I'm plugging in -89 halves or -44.5. Let's do -44.5 because that's an exact value, right? That we didn't round anything. That's exactly the same as -89 halves. Centimeters squared, square centimeters per second. Great. All right. So again, another area problem, but this time the radius, the radius of a circle is mentioned here, and the radius of a circle increases, right? So again, that's a positive, means you have a positive rate of change, positive derivative when you're increasing at a rate of 3 meters per second. So we're asked to find the rate at which the area of the circle, right? The area of the circle is increasing when the radius is 11 meters, right? And hope it makes sense that the area would be increasing, right? If the radius is getting larger, clearly the area, the circle would be getting bigger, right? So the area must be growing at a positive rate. So again, these things depend on time. Right? They change as time goes by. So the area of a circle, right? So we have a circle this time. So you may recall that the area, I'll use capital A again. Remember the area of a circle is the value of pi, right? That 3.14159 number and so on, right? It goes on more than that, but times, and then the radius of the circle, which I'll use r for radius, squared. So it's the radius squared, then times pi. And we're told, so here's a rough picture of a circle. We're told the radius is getting larger, right? So the circle would be getting bigger, and thus the area, should be getting larger as well. So we're asked to determine how fast the area is changing at a particular moment, right? The rate at which the area of the circle is increasing at the moment when the radius is 11. So again, area is a function of time. The radius is a function of time, t, right? So both sides depend on this t variable. So once again, I'll say t is time. I think they mentioned seconds here, right? And the meters per second was the rate they gave us in the problem. So just like all the other problems so far, I'm differentiating both sides with respect to this time variable t. On the left side, you got dA over dt. It's how fast the area is changing at any given time. Equals, and then here, pi would stick around, right? That's a coefficient times, and then the derivative of this radius squared is going to be kind of like powers we saw in earlier problems. It's the radius is a function of time, right? So this is some expression with t in it to the second power. So I apply the power rule, and I'm going to throw the 2 out in front of the pi here. So 2 times, r to the first power. But then afterwards, you apply the chain rule, right? Then multiply by the derivative of the expression inside. So the derivative of r with respect to t. Right? And if you want to use a prime and r prime, you could, right? So here, though, is our related rate equation. And now we go, after establishing this, now we go to our given moment. So we were given this information. So we were told that the radius was increasing at a certain rate. So dr over dt. This is the rate at which the radius is increasing. They said it was increasing at a rate of 3 meters per second. And it was positive 3. Right? So if they said the radius were decreasing at a rate of 3 meters per second, then I would say that dr dt was negative 3. So please understand that. It's very important for these problems. Increasing positive derivative, decreasing negative derivative. And then we're also, asked to find this, rate at which the area is changing when the radius was 11 meters. So you see how this gives us, 2 out of the 3 unknowns in my equation. I'll have the value of r and the value of r prime. I just, I can use it to find this a prime, right? So putting this information in to our equation here, we get, a prime on the left dA over dt equals 2 times pi times, and then the radius is 11 times, and then the dr over dt, the r prime is positive 3. And we multiply things, this is 66 pi. They said keep the pi there, enter an exact value. Now, once again, the units on this would be square meters. It's, area units in the numerator, per second, per time units, but positive, right? So this would say that the area of the circle is increasing at this rate, at this particular moment, right? At the moment when the radius reaches 11 meters and keeps expanding. So yeah, we're just saying now they have the meters squared, square meters per second units already written. You're just entering the number. So again, with the pi, right? So 66 and pi looks like it's here in the keyboard there. Wonderful. All right, so this is use related rates to solve problems involving volume. So just like, the area ones, we got, volume problems now. So now the volume of some, object here. So they explain it all, is changing with time. Right? It's more things that change as time goes on. You'll see minutes as the time units here in this question. So a trough has ends shaped like isosceles triangles, has a length of 10 meters, width of 4 meters, and height of 5 meters. So you see that picture. So width of 4 meters for the trough, this height of 5 meters for the trough, length of 10 meters, and the sides of the trough, the faces of the trough here on either end are isosceles triangles, as shown in the image below. Water is being pumped into the trough at a rate of 6 cubic meters, right? This is meters cubed, so this is a volume unit. Remember, volume is in cubic units per minute. All right, so this blue part of the picture, right? Water is filling this trough at a rate of 6 cubic meters per minute. So at what rate does the height of the water change when the water, at the moment when the water is 3 meters deep? Submit an exact answer. All right, so they're pointing out, note that the volume of a trough with length L, W, and height H is given by this formula here. is again, it would be, you know, the area of a triangle. So half base times height, half length. They call one thing the length, one thing the width, and the height. So half length times height, and then multiply that by the entire width of the whole trough. So that's why it's half length, width, height here. Okay. So again, we got this trough. Let me try my best to draw a somewhat similar picture to what they had. With the isosceles triangle faces, they said this was 4 meters. The height of it, all right, so from here to here straight up is 5 meters. And then this distance across from triangle to triangle face here is 10 meters. And it's being filled with water. So here's a filled to a little bit with water. So if you look at the face of it, so here's an isosceles triangle. All right, so let's just look at one face. So again, we got 4 meters up here across. The height of it, right, from this base perpendicular goes straight to the bottom tip there. Again, that's 5 meters. And it's filled up with water to some height. Okay, so this here, I'm going to put height. So I'm going to have h be the height of the water at any given time, because that's what we're asked about. We're asked about at what rate does the height of the water change when the water is, 3 meters deep. So the height or the depth of the water. And this changes as time goes on. And something else that would change would be, I'll call this the width of it. I think they said width. Yeah, width was 4. They called this the width of the trough up here, the 4 meters. So I'll call this the width of the water. The width across this water triangle. And that's going to change as this fills up, right? It's going to get wider, going to get bigger. Now the only thing that's not going to change is, L, the length of it, where they said the length 10 meters was the 10th length of the trough. No matter how high the water gets, the trough is still 10 meters long, right? No matter how high the water gets, the length of the water in the trough is always 10. All right, that is so that's constant. So I'm not worried about that. I can fill that in actually later. Um, but here are the only two quantities that change with time. So these are my functions of time, and again, I'll call time t. And they told us, at any particular time. So we're gonna start general. Start generally. So at any time, the volume of the water. So again, this is also changing, by the way. So I should probably have added this. So capital V will represent volume of the water as well. And this is also changing as time goes on, because obviously there will be more water, so the volume of water, the amount of water will change as time passes. So they told us, they gave this to us. at any moment, the volume of this water, the volume of the water prism here, the water trough in the trough, is half, and then they put, times length times width times height. Now, I told you that length wouldn't change, so anything that remains constant in these problems, I'm going to fill in for because they're not going to change. The only ones I care about are the quantities that actually change with time, that actually are functions of time. So again, the length is constant, so I'm going to plug that in. And so we have this relationship now. I want to establish a relationship between all the quantities that actually change as time goes on. So as time goes on, the volume of the water trough, the water in this trough will be half of 10, so 5 times W times H. And then here, this is the equation I care about. So then we're going to go from this, now I have an equation that involves all the stuff that's going to change with time, the volume, the width, the height. And we write our related rate equation, right? Differentiate with respect to time. So left side is, dv dt. And then over here, another product rule issue, right? Because again, W and H are things that change as time goes on. And I'll keep, like I did in the last problem, the 5 on the outside. I keep the coefficient around a 5 and do the product rule. So I'd have, keep the W alone times and then dH dt. Then plus, and then keep H the way it is times, and then dW dt. And here's my, related rate equation. All right. So now I need to go to our specific moment and figure out what all these things are. So they gave us that the water being put into this trough, so dV dt, changing the volume, they said water is being pumped into the trough at a rate of 6 cubic meters, right? Again, that's a volume unit per minute. It's positive, right? The volume would be increasing. The water would be there would be more and more water. So a positive rate of change. And then they told us the depth of the water. So that's the height, H. So the height of this water when it's 3 meters deep. They say find dH dt. So you might think that that's not a lot to go on. They gave us 2 of these quantities. But here's something that will make this a lot easier. The fact that they had a triangle face like this, a isosceles triangle, makes this easy, or easier. So do you see here the similar triangles? More of a geometry type problem. Okay, so you got the large triangle with a width of 4 meters, height of 5, and then the water triangle with a width of W and a height of H. So because they are similar, we can set up a proportion, W, the width of the smaller triangle, the water triangle, the ratio of that width to the width of the larger one, so W over 4, should be equivalent to the height of the water triangle, H, over the height of the larger one, 5. And then I guess I should have started with this. I just wanted to establish a related rate equation here, but if you started with this, it would make this even easier. So you see there's a relationship here between the width of this water triangle and the height. And so I can go back, all right, I can go back here into this volume equals 5 times width times height equation. I can write this solely in terms of H, and then I won't even need W or W prime. All right, if we solve for W, so at any given moment, right, these triangles are similar. The, the width of our triangle, the width of our water triangle, will be 4/5 times the height of our water triangle. So I'm going to substitute this in for W here, and then we get the volume of our water. All right, the volume of water in the trough would be 5 times, 4/5 H. W is 4/5 H. The 5s would cancel there. And so I'd have 4H and then H again. So this would be just 4H squared. And this is way nicer. Okay. So yeah, I could have started the way I did, wrote my related rate equation, but let's use this instead. I'm just going to write diff. So differentiate both sides of this with respect to t. And then you got dB dt on the left equals, and then 4 times 2h, so 8h times dH dt. And applying the chain rule. And that's enough, right? Now I went from having all these, these 5 unknowns to just 3, and they gave me 2 of them. So remember the volume is being pumped in at 6, positive 6, that's dB dt on the left, and then equals 8 times, and they told me the depth of the water was 3 meters, times dH dt, and then we can find dH dt, right? So sorry about this, I don't feel like going to a new piece of paper here. So then dH dt, when you solve for it, this is 6, this is 24, 6 divided by 24 is 1/4. And this is a height unit over time unit, and so like volume was given in cubic meters, so the height should be in meters, and time was given in minutes, so meters per minute. There's how fast, here's how fast the height is changing at that moment. The height is, it's got positive rate of change. So the height is increasing at 1/4 meter per minute at the moment when, the height of it is 3 meters. The depth is 3 meters. All right, so that was a lot there because of the similar triangles. And I saw when I did my initial related rate equation, like, hey, there's too many unknowns. They didn't give me a lot. But then if you recognize, hey, similar triangles here, I can eliminate a variable by making a substitution and make it easier going forward. Not always the easiest to see. But yeah, so that's what they want, right? The rate at which the height of the water is changing is 1/4 minute per meter at that moment. So you see they have the minutes per meter, meter per minute already there. So I'm just putting 1/4, which, it's just 0.25. I can put 0.25 exactly. That's the same exact value as 1/4. So, yeah, so they probably point that out here, and they're related. Yeah, so see right here, W, the width of the water at any given moment is 4/5 of the height, and they substituted that in, right? So, yeah, great. All right, so now we're back to a problem pretty similar to earlier. So I'm just going to fill these in. So this is just like the very first question. You have area is length times width. Area, length, and width all depend on t. So you'd have dA over dt on the left equals, length times dw dt plus width times dl dt when you apply the product rule to the right side. And they give you the length and width at any particular moment, at a particular moment, and you're filling in blanks. So again, dA dt on the left A prime equals, remember the quantity attached to L prime would be the width. So it'd be 9 there, right? They give us positive 9 for the width. 9 times the rate of change of the length plus, and then dw over dt, w prime would be attached to the length, which is 7. If you apply the product rule properly, right? So hopefully you got that down from the first question. All right, so another volume problem. This time it's the volume of a cylinder. Being quite nice again by giving you a formula, right? Instead of having to look up how to find the volume of a cylinder, hopefully recalling what the volume of a cylinder was. So a vertical cylinder is leaking water at a rate of 5 cubic meters per second. So again, this is leaking water. So that means the amount of water in the cylinder is decreasing. So I'm going to use a -5 when I talk about the rate at which the volume is changing. If the cylinder has a height of 10 meters and a radius of 4 meters, at what rate is the height of the water changing when the height is 4 meters? Okay, so this is another one where only two of these quantities, see you got volume V, the radius R, and the height H. Only two of these quantities is actually changing. So you have a cylinder, right? They told us it's a vertical cylinder, which is like this. And they told us the radius of this cylinder is 4 meters. The height of the whole cylinder is 10 meters, but we're concerned with, some water inside of it. So again, there's like this cylinder of water inside, right? Inside. And the height of that I'll call H meters. And the volume, V, right? So the amount of stuff inside here is V. And they said there's a leak, water's coming out. So the height would be decreasing, right? The amount of water would be shrinking. So they told us already the volume, so the volume of water here is going to be pi, it's the area of the circle times the height, pi r squared times h. But only volume, only V and H depend on time, right? They will change over time, right? You notice how no matter how low the water gets, the radius is still 4 meters, right? Doesn't matter how low the water gets, if you're in this cylinder, the radius is always 4. So I'm going to put that in right now, and because again, all these problems involving related rates of change. I'm really only concerned with the quantities that actually change with time, that are functions of time. Radius does not change as time goes on, so that's a constant. I can put that in. So here we have the radius squared. 4 squared would be 16, so this would be 16 pi times, just h. Then from here, now both sides depend on time. I differentiate both sides with respect to time again. So on the left side, you got this, dv over dt. On the right side would just be 16 pi, remember coefficients stick around, times, and then, the derivative of h, dh dt. And they told us it's leaking out, so the rate at which the volume is changing will be negative, and they said it's leaking out, right? It's leaking at a rate of 5 cubic meters per second. So this is what I'm going to put in for dVdt. And that's all I need, right? There's no H here. There's no other letters. It's just V prime and H prime. So the fact that they gave me that the height was 4 meters does not matter. Right? This relationship will be true no matter what the height is. So going to my specific moment, you got -5 on the left equals 16 pi, times dH dt, or H prime on the right. And so, dH over dt, what they're looking for here is -5 divided by 16 pi. And that would be height units over time units, right? So meters per second. But that's what I'm entering. It says, what rate is the height of the water changing? Now, if they said decreasing, I'd put positive because they already told me it's decreasing. They say, they tell you it's decreasing at a particular rate. So you can just put the number in, like the magnitude of the number. But they're just saying changing here, so you have to indicate, oh, if it's decreasing, put negative. If it's increasing, it's a positive. So dH over dt, the height is changing at a rate of, -5 divided by 16 pi meters per second, right? They said put in exact terms. Okay. Okay. All right, so this is really no different. All these problems in this objective seem to start the same way, at least the ones we've seen so far. Once again, you got this area equals length times width of a rectangle here. Area, length, and width all depend on some variable called t. I differentiate. You got d dt on the left equals, and that would be the length times dw dt plus the width times dl dt. So the attachment to dl dt should be the width, which would be 13, and the coefficient of dw dt would be the length, which would be 18. Right, so just once again filling in those blanks pretty quickly. Here's another one. Same thing, you're just putting in different numbers for length and width. So again, when you differentiate that side with the length times width, you're using the product rule. So dl over dt should have the width multiplied by it, so that'd be 4. And then dw dt should have the length attached to it, so that would be 8 in this problem. All right, so that objective is done. All the problems in that objective were pretty much the same thing. All right, and now we have another one where just given some abstract equation, right? Not involving a cylinder or a rectangle or a triangle or anything like that. I've done a couple like these before, very similar. So, starting with a generic equation, a formula involving these x, y's, and z's. So we have z squared equals x cubed plus y squared, and x and y and z all depend on this other variable called t. All right, so we get our related rate equation by doing implicit differentiation. We differentiate both sides with respect to this t variable, and that'll be applying the chain rule to every single one of these terms again. So we'd have 2 times z to the first, but then, chain rule times the derivative of z with respect to t, or z prime of t, equals, and over here, 3 times x squared times, and then dx dt, plus, and then 2 times y to the first, 2y times, dy dt. All right, now I have my related rate equation. go to all the information we're given. So we're given, dx dt is -2, dy dt is -3. So again, this would tell me that, the value of x is decreasing, the value of y is decreasing, right? They have negative rate. And the point xy, right, so is 4, 0. So you got to use this to find z, and they would like a positive z, once again, z greater than 0. So I put in 4 for x, 0 for y, right? Go back to the equation that relates just x, y, and z here. And you're given x and y, you should be able to find z. And that'd be z squared equals 4 cubed plus 0 squared. So that's 64. So there's two possible values of z, right? One's +8, one's -8. But, like I said, they mentioned they only want the positive value. So getting rid of that -8. So now I've got all the information I need to find dz over dt, or z prime. So popping all that information in, we got 2 times, the value of z at this point is 8 times dz dt must be equal to 3 times, x squared, so 4 squared, times dx dt, which was -2. And then this would be 0, this last term, because the value of y is 0, so I'm not going to write anything there. And then I would divide both sides by 2 times a, right? So dz over dt, the rate at which z is changing. Let's see, you'd have 3 times, this is 3 times 4 times 4. Well, that's 4 squared is 16, 2 times 8 is 16, so those 4 squared, that'll be gone, that'll be gone. You got 3 times -2, -6 would be left over. And there, again, so if x is so at this moment, where x is decreasing at a rate of 2 units per unit in t, and y is decreasing at a rate of 3 units per unit of t, z would be decreasing at a rate of 6 units per unit of t. So -6 for dz dt there. Right, so a pretty similar one, right? Just with some different powers, different numbers there, but a very similar setup to other questions in this same objective. So we have z to the 4th power must be equal to x cubed plus y squared. Once again, x and y and z all depend on some other variable called t. So we'll see how these quantities change as t changes, right? What's their rates of change? So I'm just going to put diff again here. Differentiate both sides with respect to this t variable. So on the chain rule for every term, 4 times z cubed, then times the derivative of z with respect to t, dz dt, equals 3 times x squared, then times dx dt, and then plus, 2 times y to the 1st times dy dt. All right, so we were given dx, so again, given some values here, dx dt, we were told was -1, dy dt is +3. So the value of x, so at this moment that we're looking at this particular t, this particular time, the value of x would be decreasing, but the value of y would be increasing, positive rate. And x, y is 0, 4, so x is 0, y is 4. And they want us to find a positive z once again where this all happens. All right, so this here, go back to the equation again, relating x, y, and z only, so you know x and y. You can find z. So that's z to the fourth equals, 0 cubed plus 4 squared. That's 0 plus 16. And so z could be a lot of things, some imaginary, but the only real numbers that make this work are positive 2 and negative 2. And I don't want the negative 1, right? So there's the value of z. So now I have everything I need to find the dz dt again. So I plug into this equation, we have 4 times z cubed, so 4 times, 2 cubed, times our dz over dt. Now x is 0, so this term will be gone. I don't need to know the other values there. X is 0. And then this term here is 2 times 4 for y, and then y prime dy dt is positive 3. And then I would divide by, now 2 cubed is 8. 2 times 4 is 8, so those divide out. And I'd be left with 3 over 4 for my dz dt. But it's positive though, right? So that just tells me at the moment in question, at the time in question, x is decreasing, y is increasing, and z would be increasing as well. A rate of positive 3/4 units, 3/4 units per unit of time, per unit t. So 0.75 or 3/4. Right, so that one's done. All those are pretty similar. All right, so another one, kind of like earlier with the triangle, the triangle area, right, where the base is shrinking, so a negative rate of change, and the height is increasing again, so a positive rate of change. But notice this time how the height is increasing at a faster rate than the base is decreasing. So I got this feeling that, the area will be changing. Well, I guess it depends on the moment, though. But I have a feeling that the area will be increasing at a moment we see. So we're asked about what rate will the area of the triangle change when the height is 12 centimeters and the base is 4 centimeters. All right, so pretty similar to earlier. So I have the area of a triangle, remember, is half its base times its height, where this base and height and therefore the area are all changing over time, right? They all depend on t. So I differentiate both sides. We're going to see how much these change as t changes, right? We get their rates of change related to each other. So we got dA over dt on the left. And then like earlier, I'll keep the half out here, and then we're going product rule with the b times h. So half the quantity of, you got b times the derivative of h with respect to time, dh dt, plus, and then the other way around, the height h times the derivative of the base, db dt. And then we go to what we're given, right, and plug in specifics. So we're given the fact that the height is changing, so dh dt. They said the height is increasing, so this will be a positive rate of 9 centimeters per second. They told us the base was shrinking, right? So dB dt, let's say, is negative, right? And when when quantities are shrinking or decreasing, it's a negative rate of change. So negative 5 centimeters per second. And we want to know about dA dt, find the rate at the area is changing at the moment where the height is 12 centimeters and the base is 4 centimeters. Okay, so that's 4 of these missing pieces, and it'll give me, I can plug them all in, get the 5th one. Plugging those in, the rate at which the area is changing is half of. So the base at this time is, 4 times the change in the height is, positive 9. It's increasing. Okay, so I was mistaken earlier. Looks like we're gonna get a negative rate of change. Guess it'll be so thin after a while because the height's getting so tall that the area would be decreasing here. We're gonna see a decreasing area because then you got plus, and then the height 12 times the change in the base, how fast the base is changing, which was that negative 5. Because it's so tall now. Right? It's so tall, it's super thin, so little change. It's getting to the point where it's looking like a very thin needle. Small area, smaller area as the height gets bigger. So we got half of 9 times 4, 36, plus, and then negative 60. So this is just 18 minus 30. And you distribute the half. Right, 18 minus 30, so negative 12. And this would be area units, so square centimeters in the numerator over the time units. So you got negative 12 square centimeters per second as the rate of change of the area at this moment. Wonderful. So notice they're highlighting the word decreasing here, right? So look, a triangle has a base that is decreasing at a rate of 11 centimeters per second. The height being held constant. What is the rate of change of the area of the triangle if the height is 9 centimeters? So they're telling us, so remember I brought this up in other problems, right? The height of this triangle is being held constant. So it's still the area of a triangle problem, right? Area is 1/2, times the base times the height. But they're telling us the height is constant, so it does not change with time. So I can plug those in. They're telling me that it's 9 centimeters. So because all I really want in the beginning is a relationship between quantities that change as time goes by. Quantities that are functions of time. So if I put in 9 centimeters here for h, this will be 9/2 times b. And now I have the things that are changing. Right? They told me the base is decreasing at a rate of 11 centimeters per second. And then they want to know how fast the area will be changing. So now I take this, differentiate with respect to time. So we got dA dt, or a prime of t, equals simply 9/2 times dB dt. And again, we are given that this base is changing at a rate, it's decreasing, right? So again, that's a negative rate of change, negative 11 centimeters per second. So I pop that in, and we get 9/2 times, negative 11. So that's negative 99/2. And this would be at, area units again, so square centimeters per time units. And that's what I'm entering. I could also put negative, 49.5, 49.5 square centimeters per second. I think I'll just do that. But still, negative 99/2 doesn't take that long to type there. Got it. right, then back to more of the volume stuff. So this is another thing with this one has a funnel, another thing with a picture. So water is draining from the bottom of a cone-shaped funnel. So this is a cone. And look, they even remind you of the volume of a cone. How kind. So water is draining from the bottom of a cone-shaped funnel at a rate of 0.8 cubic feet, right? Notice again, this is volume units, the change in volume over time. So leaking out, draining out at a rate of 0.8 cubic feet per second. The height of this funnel is 6 feet, right? So the whole funnel, as you can see in the drawing here, scrolling up, and the whole funnel has a height of 6 feet. And the radius at the top of the funnel, as in the diagram here, is a radius of 5 feet, right, as shown in the image below. At what rate is the height of the water in the funnel changing when the height of the water is 4 feet? So there's a blue area, right, the water in the funnel. So how fast is now, of course, if you're draining the water out, that means the volume is decreasing, so that'll be a negative rate of change. Clearly, then the height would be decreasing, and this circle on top would be getting smaller, the radius would be decreasing. So lots of things are changing here as time goes on. Okay, so I'll draw this similar picture, right? So you got this, I mentioned this cone, right? A triangular, a little circular cone here, straight up and down, right? So the height of the cone, the whole cone, right, is they said 6 feet. And the radius at the top circle of the cone here, the radius at the top, 5 feet. I won't call that R, I'll just say 5 feet. Because then you got some water, inside. And it's draining out, right? Now, in the volume, V is what's inside, right? That's how many cubic feet. So there are V, cubic feet of water inside the cone at any given time. The radius is, at the top of the circle here is R feet, right? Just R feet across from the middle to the side there, right? And then the height, which is what they're concerned with, is H feet. And they told us that the water here is draining out, so dV dt, at the rate at which the volume is changing, is negative, 0.8 cubic feet per second. We'll plug that in later, but again, don't use specifics till later. And they told us, so this volume of water, or the volume of a cone, is 1/3 the area of its base, which the base of this water cone here would be pi r squared times h, right, times the height. And all three of these things, volume, radius, height, are changing. This is going down, right? The water level would be going down. The circle on the top would be getting smaller, so the radius would be changing, the height would be changing, and of course the volume, they told us, was changing. So here's an equation relating, all these things. Now I could do a related rate equation. I could differentiate both sides, right? And I could do that, right? I could differentiate both sides of this thing with respect to time. We'd have dv dt on the left, and then this 1/3 pi, or pi over 3, is a constant. So I'll keep that out, and then we'll do product rule, with r squared times h. So that'd be r squared times, dh dt plus, and then 2r times dr dt, times h, right? So again, the derivative of r squared here, where again r is a function of time, would be 2r times dr dt, and then times h and all that there. And this is great. Now you have r, you have h, r prime, h prime, and v prime. You have 5 unknowns. Well, they didn't give us a whole lot of information though. So this is like the problem earlier with the water trough. Instead of doing this, okay, with all the r's and h's, watch, at any time, if you look at there's some more similar triangles here. Look at this straight up. Look at it, face this directly, and you're getting the following picture. And the radius at the top there is 5 feet. The height is 6 feet. So you got a right triangle in the middle here. And then you got your water. The water triangle. Still a right triangle. The same angle down here, right? So got angle, 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 similarity, right? The big right triangle and the small right triangle. It's like, and the radius is r feet, and the height of it h feet. So at any time, the radius of the water circle, the ratio of that to the radius of the big circle, or sorry, the big triangle, the water triangle, the big triangle, should be equal to the ratio of the height of the water triangle here to the height of the large triangle, so h over 6. So I can use this and get my volume equation in terms of just the height. And that's what I'm going to want to do here, because all they asked for was, at what rate is the height of the water in the funnel changing when the height of the water is 4 feet. So all they gave me was information about the height. So I'm just going to solve this for r, right? Multiply by 5. R would then be, for any time, at any t, the value of r is 5, 6 times h. So I'm going to substitute this in for r. And now we get the following, right? So at any particular time, the volume of the water here is 1/3 times pi times, and then 5/6 h, but that's going to be squared, right? That's the radius in terms of the height squared, times h. And if we, simplify this, it's be 25 pi over, 36 times 3 would be 90, and 18 would be 108. So this would be 25 pi over 108 times h cubed. And then when I differentiate this with respect to t, get dB dt on the left equals, now when you differentiate the h cubed here, it would be 3h squared times h prime, or dh dt. And you saw 3 goes into 108 36 times, so this would be 25 pi over 36 times h squared, then times, the dh dt. There's my related rate equation involving, only the height and not the height and the radius. So I'm going to use some fractions here. dB dt was given as -0.8. That's -8/10, which is, 4/5. So that'll go over here for the dB dt. -4/5 for dB dt should be equal to 25 pi over 36. And then they told us, we're at the moment when the height is 4 feet. At the moment when the height of the water is 4 feet, how fast is the height decreasing? So pop in 4 feet, so this would be 4 squared times dH dt. Right, now one of the 4's can go away, this force squared. One of those can go with this force, so this becomes 1. Then you still have a 4 here, which can go into 36 9 times. So now this is gone, and this becomes 25 pi over 9. And then I would multiply both sides by 9 over 25 pi. So when you solve this, do a little algebra, dHdt would be, negative. It should be negative, right? Obviously, the height would be decreasing. And if I multiply by 9 over 25 pi, I'd have 1 times 9 in the numerator. And then, 25 pi times 5. So 125 pi in the denominator. And this should be height units in the numerator, so feet over time units, right? So there's how fast the height is changing at that moment. It is, decreasing at a rate of 9 over 125 pi, whatever that value is, feet per second. So negative 9 divided by 125 pi. Pi is down here. Great. All right. So no picture this time, but it's like the problem that was described to us earlier. Right? This is similar to the other cylinder problem we had where water was leaking out of it earlier. So again, a vertical cylinder is leaking water, right? So the volume of water is decreasing at a rate of 4 cubic meters per second. If the cylinder has a height of 10 meters and radius of 2 meters, at what rate is the height of the water changing when the height is 3 meters? So remember, this cylinder, the radius of the water will never change, right? So the radius of the cylinder is 2 meters. The radius of the water would also be 2 meters. So the only things changing here would be the volume of the water and the height. So they gave us the volume of a cylinder, right? It's the area of the circular base times the height. But the radius they told us was 2 meters, and this would be constant, right? This is not changing as time goes on, so I'm going to sub that in there. So then the volume of the water in the cylinder would be 4 pi h, right? 4 pi times the height, 2 squared times pi times the height. Now this height and the volume do change as time goes on, so I'm going to keep these in my equation. We're going to differentiate both sides with respect to time and get our related rate equation, right? dV dt equals 4 pi times dH dt. And then this, right, the volume, they said that the water was leaking out at a rate of 4 cubic meters per second, right? So dV dt is negative 4 cubic meters per second, right? The volume of the water would be decreasing. So I'm putting negative 4 in for that, equals 4 pi times, dH dt, and then solving for dH dt, right? So then dH dt, the rate at which the height is changing, would be negative 1 over pi. Right? Divided by 4 pi, 4's would cancel. And this would be, they gave me the volume units was in cubic meters, so the height units would be in just meters, and the time units was in seconds. Okay, so there's your dH dt would be negative 1 over pi, so about negative 1/3, meter per second. But they wanted you to put it in terms of pi. So negative 1 over pi meters per second. Cool. All right, so that takes care of the 4 objectives in that first heading. So you'll notice how in the activity log here, right, that was in the heading Introduction to Related Rates and Related Rates with Volume or Area Problems. So the rest of the video will be bouncing between these two objectives here in the related rates in other applications. So still, the way you approach these does not change. You're going to identify all these quantities that are changing that depend on time or some other variable, but most of the time it will be time. set up an equation to relate those things. Then you're going to differentiate with respect to time on both sides. And then you substitute, the information given at the specific moment and find the missing piece that they want. All right. So this one involves angles or shadows. So like a street light is at the top of a pole that has a height of 17 feet. A woman 4 feet tall walks away from the pole with a speed of 8 feet per second, right? So again, notice things that are going to be changing with time here. Along a straight path. How fast is the tip of her shadow moving away from the pole? And she's 19 feet from the base of the pole. It says leave your answer as an exact number. So I'll draw a picture of the situation. This is sometimes the most difficult part, is making a diagram or a picture of the scenario being described. It's not always the easiest thing. So let's say here's the ground, straight ground there, and they have this lamp post, right? This street lamp. So, I'm not going to actually draw a big lamp or anything right there. Let's say there's a little ball of light up on the top here. We're assuming that it goes straight up, okay, 90-degree angle with the ground. So here's this lamp, street light. They tell us that this is 17 feet tall. Okay, and then there's this woman. There's a person. So there's a person over here, a woman standing, away from, not directly underneath it, but, just walking away from it. They say she's walking away from the pole. So let's say moving in that direction. The question is about the tip of her shadow. So look, a light beam comes from the lamp and would hit the top of her head. I'll just make her taller. And let's make her taller. Right there, there. Now she's taller. But they said she was 4 feet tall. So she's 4 feet tall. The lamp is 17 feet tall, the street light. And here's the light beam. And it's emanating from the light, from the lamp. Hitting, it's being blocked by her, but the light on the top of her head, hits the ground over here. So this area beneath, right, this would be her shadow. Right here, right, to where the light hits from her feet, where the light hits. So this would be her shadow. So when they talk about, the tip of the shadow, that's this point here. So it says, she walks away. There's an L in there. Walks away at a rate of, or a speed of 8 feet per second. Okay. So this distance here, okay, so the distance from the pole to the woman, that distance is increasing at this rate. So I'm going to call this, let's call this D. All right, so D, no, you know what? Yeah, I'll call it capital D. I don't want to use little d because I'm going to write little d's for the derivatives. So I'm going to have capital D represent the distance from the woman to the lamp or to the street light. So when they say she walks away at a rate of 8 feet per second, that means this distance is getting larger at a rate of 8 feet per second. So d capital, the derivative of this distance over time, the rate at which this distance is changing is positive. It's going to be growing, right? If she's going away, this is getting bigger, right? You're going that way. 8 feet per second. Feet. Now the question is about this distance here. It's about the distance from the lamp post to the from the base of the pole to the tip of the shadow. So I'm going to call this S for, say, shadow distance. So again, let's say S. This is the distance they're talking about, right? The distance from the lamp, right, the base of the pole to the tip of her shadow. And what they want us to find is how fast, as she's walking away at this speed, as this distance gets larger by 8 feet per second, if she does that, this will be a longer, thinner rectangle I just drew here, right? I got a little right triangle going on here. It'll be longer and thinner, right? So the tip of her shadow will also move away. We're trying to figure out how fast that tip point will be moving away from the lamppost. Now, maybe you see it, maybe you don't. I hope you do. But and I guess another thing. Again, hopefully you notice the similar triangles again here. I'll draw it more over here with less clutter. So here you got the small right triangle, got the big right triangle, and they share these angles, right? They share this angle. So angle, angle, side, angle, angle, angle similarity. So again, this is 17, this is 4. And then the big length I called S. And then I gotta identify this little length as well. So I'm gonna give one more letter. I'm sorry for the complexion here, but complexity. But I'm gonna call the length of the shadow just X. Right. So these are all things that are changing as time goes on, right? As she walks away, this distance would change, the length of her shadow would change, and and of course, the distance between, the tip of her shadow and the pole would change. So X is the length of her shadow. All right, so then I'm gonna call, this X here. Again, this length here, the distance from the pole to the lady, to the woman, capital D. All right, lots of stuff. So in this, right, in the small one to the big one, the ratio of, the height of the woman to the height of the pole should be equivalent to this length here of this leg, which is X over, and then the big horizontal leg in the large triangle, which is S. But what I'm going to do with X is relate it to two quantities. We're going to try to find the speed at which s is changing, we know the speed at which d is changing at the 8 feet per second. So I'm going to try to relate x to s and d here. Well, can you see how d plus x is s, right? So x is just s minus d. So I'm going to recall this s minus d. I guess I didn't need to call that x if I was just going to do this. Divided by s. And then we go through here and I can solve this for s pretty easily. Now this would imply that 4s as a proportion, 4 times s, doing cross products here, means extremes, be equal to 17 times s minus d. And then, distribute the 17 here. Take away 17s, we'd have negative 13s equals negative 17d divided by negative. So s, this is at any given moment, right? This triangle's happening, and this kind of a triangle's happening no matter where she is down the path. So the length from, from pole to the tip of her shadow will always be 17/13 multiplied by the distance from the pole to her. This will always happen. Okay, so there's my equation that I'm going to be differentiating both sides with respect to time. Because again, both these things change as time goes on, right? Her distance from the pole and her shadow tip's distance from the pole. So now I differentiate with respect to time. So then the rate of change that they're trying to ask us for, ds dt, right? This is the speed at which the tip of the shadow is moving away from the pole. It should be equal to 17/13 times the derivative of d with respect to time. So the speed at which the tip of her shadow is moving away from the pole should be 17/13 times the speed at which she is moving away from the pole, and we were told this was 8 feet per second. So 17/13 times 8, and you're asked to leave it exact. So I'm just going to 8 times, that's 80 and 56, that's 136/13. And this is in, the distance units, so in feet per second again, distance units over time units. So there's what they're asking for, right? That's ds dt, the rate of change at which this shadow tip is moving away from the pole as time passes. So if she walks away from the pole at 8 feet per second, the tip of her shadow is moving away from the pole at a little over 10 feet per second, right? This is 10 point something, almost 10 and a half. But we're asked to leave it exact, so I'm just going to leave it as, 136/13. Notice it didn't matter that she was 19 feet away from the pole, right? My related rate equation at the end only involved the rates. It didn't involve the capital D or capital S values at all. So this was 100, 136, 36 over 13 feet per second. And they try to draw, see so they're using y and x, whereas I used, s and d, right? This is s minus d in my picture. Same thing. And they set up proportions and all that. All right. So here's one involving distances. So again, being able to draw a picture, thinking about the situation. Not always the easiest thing, but if you can do it, if you can do it well, it'll make these problems that much easier. All right, so here a 13-foot ladder is leaning against the wall. So we're pulling the ladder away from the wall at a rate of 1 foot per second. So how fast is the top of the ladder moving down the wall when the bottom of the ladder is 12 feet from the wall? So they already say moving down, so I don't think I need to put a negative number here. And they already tell me it's moving down, right? So I don't think I need to put a negative. So we'll see what happens when I don't put a negative. But still, let's draw a picture. So here's the wall, here's the ground. And they say this ladder is leaning against the wall. So here's a ladder. And they say the ladder is 13 feet, right? That's never changing. And let's assume this is a 90-degree angle here. Now, this point at the bottom, they're telling us, they say we're pulling the ladder away from the wall at 1 foot per second. So if that happens, the top of the ladder would slide down the wall, right? If I pull this away from the wall, the top of the ladder would slide down the wall. So they're asking us how fast is that happening at the moment when the bottom of the ladder is 12 feet. So just like all the other problems, I'm going to try to identify quantities that are changing as time goes on. So obviously, I hope this is obvious. So I'm going to call this x. So x will represent the distance the bottom of the ladder is from the wall. So let's say x feet. You see how that would change as time goes on? And they tell us how fast it'll change, right? They're giving us dx dt is positive, 1 foot per second. And it would be positive because it's, this would be an increasing quantity. X would be growing and pulling the ladder away from the wall. And then so with this quantity. The distance from the top of the ladder to the floor, I'm going to call that y. So again, y, and this is some other quantity that is changing with time. So y is from the top of the ladder to the floor. I'll just say top to floor distance. There's a C, sorry, distance. Again, clearly changing. So we have to find, again, dy dt. Now, if you look at the picture, we've identified these things that change with time. They change as time goes on. Just remember all the other problems. You identify the quantities that change with time, and then you set up an equation involving them. So here's an equation, a relationship between x and y. You see the right triangle here. So by the Pythagorean theorem, no matter what x is, you square it, plus no matter what this y is, you square that, add them up, should be equal to 13 squared, which is 169. This should always be happening. Right. So now I take this here and differentiate, and we'll get our related rate equation. Differentiate with respect to time. I'll call time t, lowercase t. I got some power rule, chain rule terms going here. This, x squared when I differentiate will be 2 times x to the first. times dx dt plus, and then y squared, same thing, it'll be 2 times y to the first times dy dt, and then on the other side, the derivative of 169, a constant, would be 0. I know dx dt, right? They told me how fast the wall distance is increasing down here, right, from the bottom of the ladder to the wall. That's increasing at 1 foot per second. And they're talking about at the moment when the bottom of the ladder is 12 feet away from the wall. So I'll draw that picture. So the bottom is 12 feet away, and this is a 13-foot ladder. Well, now we need y, right? Because they gave me x. I'll have x, I'll have x prime. I'm trying to find y prime, so I need y. And that's where the equation comes in again, right? 12 squared plus y squared should be equal to 169. 12 squared is 144 plus y squared equals 169. Subtract 144, right? Y squared should be 25. So y is 5 feet. So at that moment, when the bottom of the ladder is 12 feet away from the wall, the top of the ladder is 5 feet from the floor. And then we can find y prime, how fast the top of the ladder is moving toward the floor. Now the 2's won't matter. Right? I can divide by 2, get rid of the 2's, right? Divide both sides by 2. So then we have x, so 12 times, and then dx dt was the 1 foot per second, plus, and then again the 2's are gone, and then y, at this moment, the top of the ladder to the floor distance is 5 feet, and then we don't know dy dt, right? And then we're solving for that. So then dy dt, I would just subtract 12 divided by 5 would be negative 12 fifths feet per second. Now this means that the distance down the wall, right, that y distance, that distance from the top of the ladder to the floor, is decreasing at 12 fifths feet per second at this moment here, or 2.4. I'm going to put 2.4. Now again, they already told me it was moving down, and they're talking speed. So since they already said it's moving down, I'm not going to put a negative here. Right? They already told me it's moving down at a rate of 2.4. And that's 12 fifths feet per second. So let's see if that works out. Yeah. So and because they already said it's moving down, it just put a speed here. It's moving down at this speed. Moving down implies that the distance is decreasing. Let me go through all that here and find, see, it's negative 12 fifths, right? Okay. So another one involving distances. Again, reading the problem, we got to set up a nice picture. So 2 airplanes are flying in the air at the same height. Airplane A is flying east at 300 miles per hour. So there's a rate of change. That'll be a dA dt, I'll call it. And airplane B is flying north at 200 miles per hour. If they are both heading to the same airport, located 90 miles east of airplane A and 120 miles north of airplane B, at what rate is the distance between the airplanes changing? So again, they got this airport. Well, it's represented with a dot. So they said this airport, 90 miles east of airplane A, right? So over here, let's say, is airplane A. And it's flying this way at a rate, and it says flying east at 300 miles per hour. And it's the airport is, 120 miles north of airplane B. So let's say airplane B is down here, and again, airplane B they said was flying north, toward the airport, the same airport, at 200 miles per hour. Okay. So the things that are changing as time goes by are the distance from A to the airport, and I'm just going to call this capital A. So capital A is distance from plane A to airport. And, again, as time goes on, this distance will also change. Right, so I'm going to call this capital B, and this will be the distance from airplane B to the airport. And since one's going directly east and the other's going directly north, this is a 90-degree angle here, we're assuming, right? And then they ask us about the distance between the planes, right? So that's between the two planes straight, draw a little segment here. So I'm going to call this capital D. This is the distance between the two planes, and that will also change, right? As these things move, right? D will get smaller. It will also change as time goes on. And so at any time, here's the relationship between these things, A, B, and D, right? Isn't A squared plus B squared equal to D squared, right? It's another right triangle. So remember, we identify the quantities, the things that are changing as time goes on. I set up a relationship to say how those quantities are related at any given time, not a specific time yet. And then we'll find our related rate equation, right? We're going to differentiate with respect to time. So we got 2 times A times, dA dt plus, 2 times B times dB dt equals, and then, 2 times D times, dd dt, the capital D, right? And I'm going to just get rid of all these 2's and divide both sides by 2. And then I'll get rid of the 2's. Okay, so we have A prime plus B prime equals D prime at any given moment. So now we go to the specific moment. Right now I'll put some specific numbers in here. They told us that the moment in question, airplane A is 90 miles away from the airport, and airplane B is 120 miles from the airport. So if you pop those in here, so D, 90 squared plus 120 squared should be equal to D squared. Let's see, that's 30. This is 30 squared It's 30 times 3, so 30 squared times 3 squared. This is 30 times 4, so 30 squared times 4 squared. Square root of that, you can pull the 30 out. So this is 30 times, the square root of 3 squared plus 4 squared equals d, and it's 5, so 150. You might have been able to tell that without doing all that junk, but so then the distance between the planes at this moment, right, when airplane A is 90 miles from the airport and airplane B is 120 miles from the airport, the two airplanes are going to be 150 miles apart. Then we can talk about their speeds. So at this moment, A 90 times, and then A prime, the speed of A is 300 miles an hour, but I'm going to make that negative because the value of A is decreasing, right? The distance to the airport is shrinking. So it'll be negative 300 for d/dt. Plus, and then B, again, B is the distance from airplane B to the airport, it's 120. Times, and then again, I'm going to call this this speed here, this dB/dt, negative 200 miles per hour, once again because B is decreasing, right? I'd be going up toward the airport and this thing would be shrinking. So again, decreasing, negative rate of change, negative 200. Should be equal to d, the distance between the planes at this moment is 150, times, and then the speed that we're looking for, d/dt. Okay. All right, so if I divide both sides by 150, then we'll have d/dt equals, now dividing each of these by 150. Now 150 is going to 300 twice, so 90 times negative 2 will be negative 180 from the first term there. And this is 30 times 5, and 30 goes into 120 4 times, and then 40, right, 5 times 40 is 200. So it'd be 4 times negative 40, that'd be minus another 160. So putting these together, that'd be negative 340 miles per hour, because it's distance over time units again. So at this particular moment, the speed at which they're getting closer together, the speed at which the distance between them is changing, the distance between the two planes, is 340 miles per hour. That's how fast they're getting closer to each other. Now they already put the word decreasing. Right? The distance between the two planes is decreasing. So since they already say the word decreasing there, it's implied to be a negative. So I'm not going to put the negative there. I'm just going to put the 340. This one's about a rocket and angles and shadows. All right, so a rocket is launched so that it rises vertically. A camera is positioned 14,000 feet from the launch pad. When the rocket is 6,000 feet above the launch pad, its velocity is 200 feet per second. So again, a rate of change there, speed. Find the necessary rate of change of the camera's angle as a function of time so that it stays focused on the rocket. Leave your answer as an exact number. So another picture where again we'll have another right triangle going on here. Because here's what's happening here, right? So here's the ground. So there's this launch pad. Right, and you got this rocket shooting straight up. There's this rocket. And then they said, 14,000 feet away. So this is never changing. So remember, you've seen this in other problems. Things that don't change, I'm going to keep, we'll keep it, we'll put it into our initial equation. So 14,000 feet away from the launch pad, there's this camera, and the camera keeps tilting. There's this angle of tilt, which I'll call theta, and it keeps tilting up and up and up to keep focused on the rocket, right? So it starts off down here and then, keeps tilting upward, 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 sweeping out this angle of theta to stay focused on the rocket. So theta, so changing with time. Again, you're identifying these quantities that change with time. Theta changes with time, that's the angle of the camera. And also the height of the rocket. So I'm going to call this h. And this is feet. And they told us it was going up at a rate of 200 feet per second. All right, so that's going to be dH dt. All right, and it's going to be positive because clearly as time goes on, h will be increasing, getting larger. All right, so hopefully you see a nice relationship between these two. All right, so theta and h change with time. 14,000 feet won't. So look, isn't so, theta is the angle here, the right triangle going on. The height of the rocket off the ground, that's the opposite side of theta. The 14,000 feet to the launch pad, that's the adjacent. Remember, opposite and adjacent, you can write up tangent. So the tangent of theta will always be equal to this height the rocket is off the ground, divided by 14,000. Opposite over adjacent. So there's an equation relating our two quantities that are changing with time. And now I'll differentiate with respect to time. So remember, the tangent of something, the derivative is the secant squared of that thing. But then, chain rule times the derivative of the thing inside, so d theta dt. And then the other side, you got, 1 over 14,000 would stick around. That's the coefficient. Times, and then simply, dH dt. Just the derivative of h. And we already know dH dt. And the specific moment in question here, specific, is when the height of the rocket is, 6,000 feet in the air. So we got dH/dt, we just need secant theta. So again, the specific moment looks like this. So again, you have this camera angle, and the rocket's 6,000 feet in the air. The base here is 14,000. Remember, secant is the reciprocal of cosine, so it's hypotenuse over adjacent. So I need the hypotenuse here. Now you can scale these down by 2,000, right? This is 2,000 times 3, and this is 2,000 times 7. Scale it down a bit and you'll have the same trig functions, same trig ratios. And so this hypotenuse, when scaled down, it's 9 plus 49 is 58, so the square root of 58. So the secant of theta, again, hypotenuse over adjacent is the square root of 58 over 7. So when I pop this into the equation here, that gets squared. So we'd have 58, all right, square root's gone, over, 49 over 7 squared times d theta dt. equals, and then over here, putting 200 feet per second in for that, you get rid of 2 of the zeros, and then 2 goes into 140, 70 times, this becomes 1/70th. And that would multiply by 49/58. So the change in angle. So how fast the angle would have to be changing to keep the camera on the rocket at this moment would be when I multiply by 49/58, we can do a little simplifying, right? This is 7 times 7, this is 7 times 10. So 7 over 580 radians, right? This is always in radians when you're doing derivatives and stuff. Radians per, let's see, they gave me feet per second earlier, so time units are in seconds. So that's how fast the camera angle would have to be moving at that moment at 7/580ths radians per second. So pretty slowly at that moment. It wouldn't have to move too quickly to keep up with the, viewing the rocket, keeping the rocket on camera. So it just says enter an exact value, right? 7/580. For distance stuff, this is pretty much the same problem as I had earlier. They're flying in the air at the same height, these planes. One's flying east, one's flying north. Just different speeds. It's just different numbers. All right, so I'll pull that picture back up. So it was this picture here, but now the numbers are different. Instead of the airplane flying east at 300 miles an hour, it's flying east at 400 miles an hour. So I'm going to say, dA dt is -400 because again, this distance to the airport shrinking. So I'm going to call it negative rate of change. The flight of, that's still 200. So this other plane is flying north at 200 miles an hour. Only this time, airplane A is 60 miles away from the airport at the moment they want, and airplane B is 80 miles away from the airport. So again, all the same stuff, right? A squared plus B squared. I called the distance between the planes D squared. So again, that's 3 times 20, 4 times 20, so it should be a 5 times 20. There should be 100 miles apart at this moment, 60, 80, 100, right triangle. So anyway, same related rate equation, right? A squared, you have A squared plus B squared equals D squared, then this related rate equation, and then I'm putting in, all these numbers. So again, A, the distance to the airport was 60, the ADT was -400 miles per hour, plus B, the distance this plane was from the airport is 80 miles. The BDT again, -200, should be equal to the distance between them, right, 100 miles at the time, times, and then this, dDdt. So dDdt, the rate, the speed at which the distance between the planes is changing, divide everything by 100 here, and be -240, and then divide that by 100, it'd be -160. So that's -400 miles per hour. And again, they probably had the word decreasing there again. Yeah, they do. So 400 miles an hour is how fast they're getting closer to each other. At that moment, the distance between the two planes is decreasing at a rate of 400 miles an hour. Again, very similar to, I didn't want to draw all that again. It's replacing that with different numbers. And this is also very similar to my ladder question earlier. So again, I'll pull that picture back up. See if I can find it here. All right, so that was, where is that? With the ladder, here it is. So here, this ladder is, it's 15 feet, leaning against the wall, pulling the ladder away from the wall at a rate of 2 feet per second. How fast is the top of the ladder moving down the wall when it's 12 feet from, when the ladder is 12 feet from the wall? So it's the same picture. I had this picture up earlier. I don't want to redraw it. So again, they're telling us the ladder is now 15 feet long, so that's not changing. I got this X feet away from the bottom of the bottom of the ladder to the wall, X feet. That's going away at 2 feet per second now. And from the top of the ladder to the floor, and I called that Y feet, and X squared. So now X squared plus Y squared should be equal to 225, right? 15 squared this time. And so when X equals 12, this is the specific moment. Now we still have the same related rate equation from here. All right, this would still be the same related rate equation. If I differentiate both sides of this with respect to t, I'd get xx prime plus y prime equals 0. And at the moment where x equals 12, right, we're seeing this, again, 15-foot hypotenuse, 12 feet there. So you'd have, 144 plus y squared equals 225. Subtract 144. So y squared would be, 81 is 3 times 4, 3 times 5. This would be 3 times 3, so 9. This would have to be 9 feet. So then x is 12. Dx dt is, positive 2. X would be increasing here. Plus, and then, the y would be 9. And then dy dt, we don't know. That's what we're trying to find, equals 0. And so dy dt would be, this is 24, negative 24 divided by 9. But that's 3 times 8, 3 times 8, so negative 8 thirds, feet per second. And again, they probably have the word down there already. So yeah, the ladder is moving down the wall at a rate of 8 thirds feet per second. Right. So again, a lot of similar problems here, just changing the numbers up. So if you went over my ladder problem earlier, right, it's very similar. You're just replacing new numbers. All right, so this is a little different than the rocket problem. That's another one where you're talking about how fast an angle needs to be changing. So you are stationary on the ground and are watching a bird fly horizontally towards you at a rate of 5 meters per second. The bird is located 40 meters above your head. So how fast does the angle of elevation of your head change when the horizontal distance between you and the bird is 170 meters? So another picture, right? So here's the ground. So here's you, or the person. It said you are stationary. So you're on the ground. There's a bird in the sky flying toward you horizontally, right? So flying this way. And here's the horizontal distance, because they mention this horizontal distance between you and the bird, not the actual distance between you and the bird, but they say when the horizontal distance between you and the bird is 170 meters. So I'll call this h for horizontal distance. That's going to be changing, right? The bird's going this way at 5 meters per second. So this, again, this could be h up here as well, directly above you. So this is also h, just make a little rectangle here. 90 degrees all around. But that's obviously changing as time goes on, right? H would be shrinking, this horizontal distance if it's flying towards you. And then you have the angle of elevation. So again, that's what angle off the horizontal would I have to look at the bird and it says it's 40 meters above your head. So let's just assume this is my head, right? This is, so your head is this dot, your head. So it's 40 meters above your head, flying toward you. All right, so that's going to stay fixed. This 40 meters, again, they're saying the bird's flying horizontally. So this is, I'm going to keep this as 40, right? That's not changing at all. What would change though is, again, the angle of elevation. The angle that you have to tilt your head to see the bird. So this theta here, angle of elevation. So the things that change as time goes on are theta and h. And then very similar to the rocket problem, can you see that? Hopefully you can see the right triangle here. Got this angle, opposite length 40 meters, adjacent length h. So the tangent of this angle is going to be, 40 divided by h, right? Opposite over adjacent. Or, if you don't like that, you could say the cotangent, just to have h not in the denominator. You could say the cotangent of theta is just the reciprocal of that, right? H over 40. And honestly, I'd prefer this just because I don't want, you can keep h in the denominator, but I'd rather it not be. All right, so we'll go from here. All right, so I'm gonna differentiate both sides of this with respect to t. So remember the derivative of the cotangent of something was, the opposite of the cosecant squared. So negative cosecant squared theta, but then times, chain rule the derivative of theta with respect to t equals, then over here just 1/40th times dH dt. Okay. So now we're at a specific moment, right, when the specific moment in question is when this horizontal distance that the bird is from you is 170 meters. So that'll be the h. So at that specific moment, here is my triangle. So again, the angle theta, the height off the ground is 40 meters. Horizontal height there, again, we can just scale this down to 4 and 17. So then the hypotenuse, you'd have, 16 plus 289. 16 and 289 be 305. Yeah, so this would be the square root of 305 for the hypotenuse. So then the cosecant of theta at that moment, remember this is the reciprocal of sine, so it's hypotenuse over opposite, so over 4 here. So when I pop this in and we square stuff, so let's take this up here. We'll have the opposite of, now cosecant squared will make this 305 divided by 4, or 16, sorry, 4 squared, times d theta dt equals, and then 1/40th, and then dH dt, right, was -5, because again, h will be shrinking. So I'm going to call this -5 meters per second. So that turns this right side here into -1/8, because 5 goes into 48 times. And then I would multiply both sides by -16 over 305. So now we have d theta dt was positive, 2 over 305 radians per second. Yeah, second. Again, it's angle measure in radians over time units. So again, a pretty tiny number, right? It means you wouldn't have to tilt your head too fast, right? To keep up with it, to keep your line of sight in line with the bird. So d theta dt 2 over 305 radians per second. Okay, this is very, so I did the one with the shadow tip earlier. Let me pull that picture up. So, I don't feel like redrawing all this. So I had this picture up earlier. And you got the lamp post, which is, again, 17 feet tall. This time, though, the woman is 5 feet tall. She's walking away at 8 feet per second again on a straight path. And the question is, how fast is the tip of her shadow? So again, dsdt here. How fast is the tip of her shadow moving away from the base of the pole when she's 18 feet from the pole? So again, the picture here, instead of this being 17 and 4, this is 17 and 5. Again, I called D the distance from the woman to the pole. X was the length of her shadow, which was just S minus D. Again, S was the distance from the pole to the tip of the shadow. So I had this proportion here, where now this would be 5 over 17 with these similar triangles, equals S minus D over S. So then 5S would be 17S minus 17D, 5S. And subtracting 17, this would be negative 12 instead. So instead of 17/13 D for S, you have 17/12. So this would turn into 17/12 instead of 17/13. And then times 8, right? Again, the speed at which she's walking away from the pole is still 8 feet per second. So we can simplify this a little more. So it'd be 136 over 12, but this is 2 times 4. This is 2 times 4, this is 2 times 6, this is 2 times 2, this is 2 times 3. So we got like 34 thirds feet per second is how fast the tip of the shadow is moving away from the base of the pole. It's the same thing as earlier, just change her height from 4 feet to 5 feet. So 34 thirds feet per second for this one. Okay. And very, very similar stuff, just different numbers. And great. All right, so hopefully watching me go through all these problems here helps you in some way when you work on the assignment on your own. Thank you very much for watching.